Okay then, now we are ready for part 2, where we have our first set of variations on the idea of completing the square. What we saw before was the easiest of cases, and now we have something that presents a little bit more challenge. Next example, y is equal to x squared plus 2x minus 5. Okay, so I'm still thinking to myself, 2a is equal to 2, a is equal to 1, a squared is equal to 1, but I don't have a plus 1 here. Instead, I have a minus 5. Okay, so let me think a little more, and I think, okay, if I had, what do I need? Y is equal to x squared plus 2x plus 1 minus 1 minus 5. So I am interjecting right here what I need. Now, what I have here is just the number 0. So I am adding 0 to the original equation. So how does that come out? Now I'm going to group things a little bit differently. I group the part that is the perfect square, and I write, okay, so this y is equal to x squared plus 2x plus 1 minus 1 minus 5. That's what's left. So now I have x plus, plus 1 squared minus 6. And what I'm telling you here is this, that this equation and this equation are the same. And I think it would be a fine idea to check this in your calculator or in Desmos and see that they are the same. And how I did this is by choosing very carefully a form of the number 0 that was going to make things come out the way that I want them to. And a whole lot of scribbling, which may be making it a little hard to read, so let's try another example. Okay, y is equal to x squared minus 6x plus 4. Okay, now what I need with this minus 6x, since 6 is equal to 2 times 3, I need y to be equal to x squared minus 6x, and since 3 squared is 9, plus 9. Well, I can add 9 provided that I also subtract 9 so that in the end I am adding 0. Okay, so let's use some hot pink here to decorate my 0. It is 0 after all, isn't it? Okay, so I have x minus 3 squared minus 9 plus 4, or x minus 3 squared minus 5. And we also know that if we graph this and this, since the only difference between them is 0, that they're going to have the same graph. And besides that, when I look at this, here's a mathematician's eyeball looking at that. I don't know what it looks like. I don't know what the graph looks like. When I look at this, I do know what that graph looks like. It's an everyday parabola, moved 3 units to the right and 5 units down, so that it's something like that, with the vertex at 3, -5, and we'll have more to say about that in a few days. Okay, so that's the first variation that we have. No, one more problem. This type, let's see. Y is equal to x squared minus 4x plus 1. Well, 2a, I think to myself, is 4, so a is 2, a squared is 2 squared, which is 4, but I don't have enough here. So I'm going to add a very carefully chosen form of number 0 plus 4 minus 4 plus 1. Okay. Now I can factor the part of it that's on the left into x minus 2 squared, and I have minus 4 plus 1 left over. So ultimately x minus 2 squared minus 3. And again, this is something that I can graph. I can think of the graph. All I got to do is think of it, and I see it in my mind automatically, which is something I can't do with the one up above because I'm not that good. But I'm this good, and this really does give me a feeling of power. Okay, so that's variation 1, the end up. Okay, onward. Variation 2. Suppose that what life gives you is just y is equal to x squared plus 4x. And there isn't any constant here, but I can put one there, can't I? The constant that I would like for, if 2a is 4, then a is 2, and a squared is 2 squared, which is 4 again. X squared plus 4x. Now, if I add 4 so that I can complete the square and subtract 4 because I added 4, I have added 0. So now I can factor the stuff on the left, x plus 2 squared. So that takes care of this much. And then I have minus 4 left over. So I'm adding 0 here. I'll put the 0 in quotes if you like, or if you don't like. Next, another example of this one, y is equal to x squared minus 8x. Okay, if 2a is equal to 8, then a is equal to 4, and a squared is equal to 16. So to make this part into a perfect square, I need to add 16, but in order not to change the equation, I also need to subtract 16. So now I have a perfect square, x minus 4 squared on the left minus 16. And life is good. Okay. That's the end of variation 2. I think we have 2 to go. Okay. Variation 3. you might have noticed that every time we did this, we picked a number that was even to go next to the x in the middle. But as we know, not all numbers are even. So let's choose an odd number. Suppose we have y is equal to x squared plus 3x plus 1. Well, maybe not all numbers are even, but all numbers are divisible by 2. If 2 times a is 3, then a is 3 over 2. And all values a can be squared, so I have 3 halves squared, which is 9 over 4. Okay, I'm going to do the same thing. I have x squared plus 3x. And you know by now that I'm going to add and subtract something right there. I'm going to add 9/4, and I'm going to subtract 9/4. So that gives me x plus 3 halves from over there, x plus 3 halves. I square that. Now I subtract the 9/4, and I still add 1. And from that, I now have x plus 3 halves squared minus 5 over 4. Well, ordinarily we choose nice big fat round numbers, but we can move this left 3 halves and down 5/4 when we graph. One more of this type. Suppose we had y equals x squared plus x plus 1. Looks like we can factor it, but we cannot, because if this were a perfect square, it would say x squared plus 2x plus 1, not just 1x. So 2a is equal to 1. A is equal to 1/2. A squared is equal to 1/2 squared, which is 1 over 4. So now I'm going to both add 1/4 and subtract 1/4. Everything else stays the same. Now I have stuff on the left that I can factor. X plus 1/2, this 1/2, squared, minus 1/4 plus 1. So our original will graph this way, x plus 1/2 squared plus 3 over 4. There we are. And we could check that by FOILing. Okay. I believe that will do for, let's see, this is the end of part 2.